and you can go ahead.
Thank you very much. Thank you everyone for being here. My name is Ilaria Caiazzo. I'm a postdoc at Caltech. And today I'm going to talk about some work that I've been doing on white dwarfs with my collaborators here at Caltech at the University of British Columbia. And in particular, some work that I've been doing on magnetic white dwarfs. So we've heard already about magnetic white dwarfs last time from Nikolai's talk, but for people that were not here, just let me quickly introduce them again. So we know that a big percentage of white dwarfs appear to be magnetic, between 50 and 20%, and they show a huge range of magnetic fields from a few tens of kilogauss up to almost a gigagauss. And it's still a mystery why only some white dwarfs appear magnetic and some others don't. And where is this huge range and huge diversity in fields is coming from? So there are, of course, different possible explanations, and you can kind of divide them into families. So the ones that explain the field from evolution and the ones that explain the field from interaction. And of course, the easiest and more obvious one is, magnetic progenitors. We know that there are some main sequence stars that show very strong magnetic fields, and so it would be natural for them to produce magnetized remnant. However, there's not enough of them to explain such a big percentage, so it cannot be only that. And then the magnetic field might be still hidden in the progenitor. It might still be in the progenitor, but hidden in the cores, in the convective core. So you don't see the magnetic field, but the magnetic field is there, and then it shows up in the remnant. Or there's a possibility that has been proposed quite recently that the field could be produced when the white dwarf freezes, so when the core of the white dwarf crystallizes. And then there's the other family, which is what the magnetic field comes from interaction, and in particular from the dynamos that arise during accretion processes or during the merger of two white dwarfs. And during this talk, I'm going to mainly focus on this last one, so the mergers of two white dwarfs, and how we're looking for merger remnants. But before I get into that, I like to just say that not all of this process, or at least some of this process, might all be happening, and it might all be at work, and might generate maybe different type of magnetic white dwarfs. And so let me digress just for a minute and tell you about some white dwarfs that we found in open clusters with my collaborators at UBC that already show that mergers, even if we do expect mergers to create highly magnetized white dwarfs, they are not the only process at work in creating magnetic white dwarfs. And these young magnetic white dwarfs that you find in open clusters are very interesting because they tell us a bit about what processes cannot be at work here. And I'm just going to go over this here. You can see the initial final mass relation. The initial is the mass of the main sequence stars, and final is the mass of the white dwarf. And so we were looking for white dwarfs in young clusters that are producing massive white dwarfs, and we found a few that you can see here in red, and 3 of these white dwarfs turned out to be magnetic. They were in these 3 clusters, ACC 47, Messier 39, and Messier 47, which are all young clusters around 100 million years old. And so these newly found white dwarfs in open clusters already tells us that in this particular case, the field cannot be produced by crystallization because these white dwarfs are very hot. One of them is actually 100,000 degrees, so very, very hot. The clusters are too young to have produced white dwarfs that could merge and not explode, because they're producing right now white dwarfs that are around 1 solar masses. And so if you merge 2 white dwarfs that are around 1 solar masses, then you're above Chandrasekhar. It's hard to create a merger remnant. And then there's no indication of a companion whatsoever for these objects, and the clusters are very, very small binary fractions, as you can see here in the CMD. And so accretion in binary interaction is also very unlikely to have happened for all of them. And at the end, so the fraction that we found is, in this region is 3 out of 6. And therefore, it's very hard, again, to explain it with magnetic APBP stars because they're quite rare compared to this high percentage. And so you can already see that so these 3 white dwarfs that we found are quite interesting because they really tell us that at least some white dwarfs are born with magnetic fields. So some white dwarfs have fossil fields. But okay, after this small caveat, I would like now to go to actual mergers of white dwarfs, which, as I said, we still believe that they create at least some of the magnetic white dwarfs because of the very strong dynamo that happened during the merger. And so it would be interesting. So at Caltech with ZTF, we are trying to find these merger remnants to study their characteristic. And how do you find a merger remnant? So I already said you expect them to be highly magnetized. And the merger of 2 white dwarfs, you expect them to be more massive on average. And the third characteristic that would make a white dwarf a very likely candidate for being a merger remnant is if it's rapidly rotating. Because when you have a merger, you expect some of the angular momentum of the binary to be conserved in the final product. And so if a white dwarf is highly magnetized, the surface emission is not uniform, it might be spotted, and therefore if you have a non-uniform surface emission on a rapidly rotating object, the object could be found through photometric variability. So they might show photometric variability. And that's why the Zwicky Transient Facility is a great instrument, a great tool to find highly magnetized and rotating white dwarfs. And this is exactly what we are doing with ZTF. So for those who don't know ZTF, it's a synoptic optical survey that is based in Palomar on the 48-inch. It looks at the entire sky almost every night. It has a huge field of view of 47 square degrees. And it's been an amazing tool at finding transients, supernovae, TDEs, etc. But it's also amazing to look for variable stars because it really quickly accumulates hundreds of epochs. And then we have this team at Caltech that has developed pipelines for photometric analysis and for period searching. And so we can search for periodic variables among all of the source observed with ZTF. And so we can find a lot of variable white dwarfs. And so this is our search. So we focused mainly, so this is some of the candidates that we found here in white. I'm going to show the full sample later. We decided to focus our search on the massive part of the HR diagram here for white dwarfs, simply because it's easier at the beginning. We're looking for mergers, so expect them to be massive. And also in this way, we kind of avoided most of the contamination from pulsators and other types of variables. And so we looked for, here is an example of the type of light curves that we observe with ZTF. So either sinusoidal or multi-peaked, and they usually look like these, or a little bit simpler than these, just sinusoidal. And that's because what we're looking here is mostly a spotted white dwarfs. And of course, when we find a variable white dwarfs, and we were looking also for a rotation period of about a few minutes to a few hours, which is about what you expect for merger remnants. And so when we found our candidates, of course, to figure out if where the variability is coming from and if they're actually magnetic, we took spectra, mostly with Keck, with Elris and Keck. And so I'm just gonna show you quickly what we expected to find and how a magnetic white dwarf looks like in spectroscopy. So here on the left, you can see several spectra of hydrogen white dwarfs with fields of a few megagauss and with some intermediate magnetic fields. What happened is that the absorption lines get splitted into 3 components. And depending on the strength of the field, the components becomes more and more separated in wavelength. But for higher fields, the situation becomes a little bit more complicated. Here on the right, you can see the prediction of the location of the Balmer lines with the different magnetic field strengths. And here's H alpha, beta, and gamma. And you can see that around a gigagauss or a bit more, you mainly have this split in 3 that we see here as well. But as you go to higher and higher field, it becomes more complicated. So there's not more the linear Zeeman splitting, but it becomes split in more components, and the components get shifted in wavelength. And for this reason, it's a bit harder to find highly magnetized white dwarfs from their spectra. You can see here some of the spectra, and you can see these spaghetti plots in which you look at where you expect the Balmer lines to be, and you try to identify these various strange features as absorption lines in this strong magnetic field. And usually the type of features that you find is when a line, as you can see here, this one, for example, when you have a line that has a minimum or a maximum in wavelength, like here or these ones, and that means that the location of the absorption line doesn't change very much with changing fields. And therefore, even if the field changes quite a lot on the surface of the white dwarf, you're still seeing the features, so it doesn't get completely washed out. And so those are called stationary line, and this is what you usually look for to identify magnetic white dwarfs with spectra. And so this is just to introduce you to what we're going to look at next, which is, but first of all, our first result. One of the first objects that we found is ZTF 1901+1458. It's an extremely blue white dwarf that you can see here in the Gaia CMD, and this is a Panster image. It's very, very, very blue. And we found it to be periodically variable with a period of about 7 minutes. And here you can see the light curve. This is the ZTF light curve, and this is the Chimera light curve taken with the 200-inch at Palomar. And you can see it's quite a simple, almost sinusoidal light curve with a strange difference in phase between the G and the R filter. And yes, our discovery has been accepted now. The discovery paper has been now accepted in Nature. And the reason why this object is so interesting is, of course, because it's very rapidly rotating, and it shows an extremely strong magnetic field, as you can see here. So this is the spectrum in the blue and the red. This is the spaghetti plot that I was talking about before. And you can see that we were able to identify several features, mostly stationary lines, that pinpoint a magnetic field on the surface of about 800 megagauss, which is very high, is one of the highest found for magnetic white dwarfs. And on top of that, as I said, this object is extremely blue. And so we fitted the photometry. We got UV photometry on top of the Panzer's photometry in the optical. And we fitted the photometry to get a sense of the temperature, which is about 80,000 degrees, and the radius. So we can obtain quite a precise measurement of the radius because the Gaia parallax is very, it's very accurate. This object is only at 40 parsecs away. It's not, it's not far. It's very, very close. And so it has a very precise parallax. And so we can get a radius of about 1,800 kilometers. And you know, all of you know that white dwarfs, typical white dwarfs, have radii of about, you know, the radius of the Earth are a little bit bigger, while ZTF 1901 has a radius that is practically the radius of the Moon. So it's extremely small. And so it's probably the smallest white dwarf found until now. So it's the closest found to the Chandrasekhar mass. So because depending on the composition that you assume, it has a mass between 1.35 to 1.37 solar masses, so very close to the Chandrasekhar mass. And finding a white dwarf that is so compact is quite interesting because at such a small radius, the density in the core is probably high enough that this object is undergoing electron capture on sodium in the core. Here you can see the mass radius relation for different compositions, and this M1 is the composition of oxygen neon that you would expect in the core, oxygen neon, magnesium, and sodium that you would expect in the core of the white dwarf. This is from the Kamisasa models. And here, this is the dotted line, and the solid line, it shows the same composition, the same mass radius relation, if you include the effect of electron capture. Because as you know, the pressure in the white dwarf is given by the electrons. And so if you start removing electrons through electron capture, you're removing the pressure support, and therefore the white dwarf shrinks. For the same mass, you have a smaller white dwarf. And here is where our white dwarf is in this purple region. And you can see that here is the threshold for the density threshold for electron capture in sodium. And you see that we are already above that threshold. And this is where the white dwarf is right now. But you know, as more sodium sediments in the core of the white dwarf, this process will still keep going because, of course, this white dwarf is now very young, probably a few million years old, and as the white dwarf sediments, if the element sediments in the core, more sodium will go in the center past the threshold for electron capture. So the white dwarf might still keep shrinking in the future. And right now, the fact that there is this electron capture going on in the core means that this white dwarf is mainly cooling through neutrino emission due to Urca processes, which is quite different from normal white dwarfs. I think I'm almost out of time. So the thing is that if you have this electron capture going on for, if more sodium sediments and you keep having electron capture, the white dwarf keeps shrinking, it might get to a point in which the pressure is just not enough to support the mass of the white dwarf, and the white dwarf might collapse in the future. This is very uncertain because it depends on the time scale of sedimentations and freezing. Because if the white dwarf freezes, then there's not going to be any more sedimentation of sodium, and so this process will stop. And so we don't know what's going to happen. It's likely that the white dwarf will actually not collapse, but if it does collapse, it's interesting because it will create a millisecond pulsar, period about 20 milliseconds, and normal magnetic field. And this could be a different way of creating neutron stars that could explain, for example, why we see some young pulsars in globular clusters, for example. They could be born in this process, and this object is only 40 parsecs away. So if something like this is real, so if this is going to happen, if the white dwarf is going to become a neutron star, then a big chunk of neutron stars are born in this way. So just show you a few other objects that we're finding. You can see here the spectra. You have we are finding some highly magnetized white dwarf. You can see here, this is 100 megagauss with a period of an hour. This is 19 minutes with a field of 175 megagauss, etc. So we're finding many of these objects with very high fields and small periods. They're all interesting candidates for being white dwarf mergers. And then we have even some other type of objects. Not here, I was only showing DAs, so hydrogen white dwarfs. But we also have carbon white dwarfs. This is a hot DQ that we have found that is variable in the same region of the CMD. This is probably a helium white dwarf, as you can see from the strange spectrum. These are most likely, around 50 megagauss. Helium white dwarfs. And then we're finding even other strange objects that I still all very preliminary, so I don't want to get too much into it, also because I don't have much time. But you can see here, for example, we have two objects with very strange features that might be the first indication of a cyclotron absorption on magnetic white dwarfs, on isolated magnetic white dwarfs, which is very exciting. But again, this is all kind of preliminary. We're still going through all these objects that we're finding and trying to understand and model their spectra. But here is like kind of summary. We are putting together a large sample of bona-fide merger remnants. So rapidly rotating, highly magnetic and massive white dwarfs. And of course, maybe not all of them will be mergers, remnants, but finding such a sample, it's interesting because it can tell us a lot about the properties of the merger remnants, their chemical composition, their evolution, the delay time between the formation of the binary and the actual merger. And of course, it can, we can help us understand the merger rate in the galaxy. And then what's the contribution to the supernova 1A rate, because these are like the ones that are like very close to be supernova, very high massive, but just not enough. And then of course, understand magnetic fields in white dwarfs. So I think I'm out of time now, so I'll finish here. Thank you very much.
Thanks, Ilaria. That was really cool stuff. Let's take questions now. And there is already a question in the chat by Frederick. Could the difference in photometric phase in the blue and green be due to different effective field strengths? How many spectra do you have? Could you see phase-dependent changes?
That's a very good question. We do have phase-resolved spectra. So the difference in photometric in phase, it could be, I was thinking that could also be due to the fact that there might be hotspot or gradients on the surface that have different colors, right? And that's why we see a different temperature, different colors, and that's why we see sort of a difference between the two filters. But yeah, we do have phase-dependent spectra, and they show small differences. It depends on the objects. For 1901, the differences are not very big, but we can see the lines moving, some of the lines moving, because, and so we can actually figure out that the field on the surface has a big range between 600 and probably 900 megagauss. So yeah, we do see changes, and they're due to the difference in magnetic field over the surface.
Nicole has her hand up, so go ahead, Nicole.
Hey, I'm wondering, because above, like, let's say 40,000 Kelvin, you cannot really fit the temperature of a white dwarf via an SED. So what are your errors on the temperature you assumed, and what are consequently the errors on the radii and on the radius and the mass of your tiny white dwarf?
What do you mean that you cannot fit it photometrically above 40,000?
Because the SED is no longer sensitive to changes in the effective temperature above 40,000. So when you
but we have UV photometry.
No, that doesn't matter. It's still the Rayleigh Jeans part of the flux distribution. So you can see when you fit the photometry and compare that to results from the spectral analysis, that the values, they do not agree. So I'm wondering what you assumed there for an error.
We just fitted the spectra from Pierre-Emmanuel Tremblay on the photometry, and we get an error from the covariance of the fit. It still, of course, it's the Rayleigh Jean scale, but you still can get a fit given by the
but
slope.
that you cannot trust. And also you don't assume magnetic fields in the models.
Yeah, so the thing is, yes, so the constraints on the radius come mostly from the distance, the fact that it's so close, and you just get, from the brightness of the white dwarf and the distance. Changing the temperature in the white dwarf might change the radius a bit. The errors just come from the fit, the ones that are, I don't know if I was showing the errors, but the errors come from the fit, and they're quite tiny. But the change in temperature does change the result on the radius, but not enormously, because we still see that you're in the Rayleigh Jean, so you still know that the white dwarf is very, very hot. Yes, of course, there's the problem of the fact that the white dwarf is highly magnetic, and for this reason, we actually are asking for HST spectra, because we still don't understand completely the SED of magnetic white dwarfs. So of course there is some uncertainties in that as well. So yes, the errors on the fitting are quite small. The errors on the modeling are much larger, and that we can do. This is the best we can do. And so the next step is actually getting UV spectra to understand. There's some magnetic white dwarfs, for example, that show very, very strange SED in the UV, and some white dwarfs that don't. And so, for example, getting UV spectra is going to help in that sense. But yeah, the modeling, we did the best that we could, but of course there are modeling errors that we cannot control.
Short question from Tomasz before I move on. What's the shortest spin period you have found so far?
Tom, thank you for the question. This is still very preliminary, as I said, but for now it's 3.8 minutes. But we still need to have some follow-up on that one, so might change, but no, the period won't change. But we still have to understand that is for sure a magnetic white dwarfs, but that's the smallest period we've got so far.
Thank you.
That's great. There's more questions, but I'm afraid we have to move on. So maybe you can answer them on the chat or Slack later. So thanks, Ilaria.
Thank you very much.